This is part 2 of the Chapter 19 lecture outline. This portion of Chapter 19 it goes into very specific examples of different types of severe weather, specifically thunderstorms, tornadoes, and hurricanes. Your book does a great job going through this content. I will go through most of these slides, and a lot of them are just pictures showing you different features of the thunderstorm, tornado, and hurricanes. So I won't be adding much to this slideshow. So just some features for thunderstorms. They feature cumulonimbus clouds, heavy rainfall, lightning, and occasionally they feature hail. I talked about how hail is formed in a previous chapter. So at any one time, there's about 2,000 of these in progress, and we have about 100,000 of these per year in the United States, and they're most frequently occurring in Florida and the eastern Gulf Coast region. So the average number of days per year with thunderstorms, you're going to see there's places in the United States that barely have any. The western coast of the United States rarely has thunderstorms, and the biggest area of the country that has these thunderstorms would be the Midwest locations and locations in Florida and along the Gulf Coast. So all of them require moist air, warm air, and instability, which all that means is the air is going to be lifting and increasing in altitude. So you have high surface temperatures, and because of this, it's most common that these will occur in the afternoon and early evening. They require a continuous supply of warm air and moisture because as the air lifts, you have to. These cumulonimbus clouds require a lot of moisture and warm air to form and become very high in altitude. So each surge causes air to rise higher and higher, creating what's called updrafts and downdrafts inside the cumulonimbus cloud. And eventually precipitation forms, and this is where you're going to have the most active stage of the thunderstorm, where there's gusty winds, lightning, hail, and heavy precipitation, typically in the form of rain. And afterwards, there's a cooling effect, which marks the end of the thunderstorm activity. So thunderstorm development. I'll let you read through the chapter on this, and this is actually a really good slide that talks about how these thunderstorms are formed. But just remember, there's always going to be this instability in the air, lifting up, reaching a point where your relative humidity is 100%, then you're going to have condensation forming. So just the same idea of cloud formation is the same way thunderstorm development works. It's just in one extreme case where you have lots of moisture creating a lot of precipitation. So tornadoes. So these are local storms of short duration. They usually feature a violent windstorm, rotating columns of air that extend down from a cumulonimbus cloud, and the low pressure inside causes the air to rush in the tornado. And winds could approach 300 miles per hour in a tornado. And these smaller suction vortices can form inside stronger tornadoes as well. And these occur most frequently in the months of April through June, and they're also associated with severe thunderstorms. The exact cause of tornado formation is not known, but there's a lot of science that goes into these, and they're studied immensely in the meteorological world. So tornado formation, again, this is a best guess as to how it forms. So essentially what you have is you have strong winds aloft, so higher in altitude, and then weaker winds below. What that creates is a strong updraft. So this rotating column of air eventually rotates so that it's perpendicular with the ground, and this rotation continues and sometimes forms a suction vortice that can hit the ground. So they most often occur along a cold front during the spring months, and they're associated with large thunderstorms, which are called supercells. So the characteristics of these supercells would be a diameter between 500 and 2,000 feet. They speed across the landscape very fast at about 30 miles per hour, and they cut a long path, usually about 6 miles. The maximum winds in supercells can range beyond 310 miles per hour. There is a scale for tornadoes called the Enhanced Fujita scale. So if you've ever seen a tornado given a rating, it's usually the EF scale. So this just talks about the different scales and the different ratings, where the EF5 is the most severe tornado that is possible. So tornado occurrence, again, typically during the late spring, summer months, and there's at different locations in the United States you would have more tornadoes. And these are very infrequent. All right, tornado destruction. So the next few slides, there's just a lot of pictures about tornado destruction. It really depends on the strength of the wind and also the strength of the structures that are in the path of the tornado. So most injuries and deaths are caused from flying debris, and fewer than 2% of U.S. tornadoes result in fatalities, usually because meteorologists can see these things coming. Tornado warnings and tornado watches are always issued when a supercell is formed, and Doppler radar can actually see that these things are happening. And these are just some pictures of tornado damage. So a tornado watch is just a way to alert the public to the possibility of tornadoes, and they are issued when the conditions are favorable. And they cover a huge swath of areas, upwards of 25,000 square miles. A tornado warning is issued when a tornado is sighted or is indicated by weather radar. So this is just an example of what a tornado would look like using Doppler radar. So a hurricane is the last severe weather pattern that we're going to talk about in this chapter. This is where wind speeds are in excess of 74 miles per hour. This is a rotating cyclonic circulation, so it's typically associated, well, it's always associated with a low pressure system, and they always tend to form between the latitudes of 5 to 20 degrees. So there's only certain regions where hurricanes can form, and hurricanes are called different things depending on where they originate on the planet. So if we ever had a hurricane come in Scranton, we would call them a hurricane, but we call them typhoons in the Western Pacific, and if they happen in the Indian Ocean, they're just called simply cyclones. So the North Pacific has the greatest number of hurricanes per year. So the different parts of a hurricane: the first would be the eye wall. So this is near the center eye of the hurricane. It's an area associated with rising air because it's at the location of the low pressure system. You have intense convective activity, which just means you have intense instability with rising air, and it's usually a wall of cumulonimbus clouds. So just picture a thunderstorm cloud, but a big wall of them around a circle, and that's basically what the eye wall is. This is where you have the greatest wind speeds and the heaviest rainfall. The eye is at the very center, about 12.5 miles in diameter on average. There is no precipitation in the eye, and it's actually quite sunny and fair inside. The winds subside, and the air gradually descends and heats by compression, and this is always the warmest part of the storm. So this is just a satellite photo of a hurricane, specifically a super typhoon. So the eye wall is surrounding a well-developed eye where the weather inside the eye is fair and sunny. So the cross-section of a hurricane will show you all the different pieces and show you the rotation of the wind. It's essentially just a large, low-pressure cyclone where severe weather has formed in different regions of that cyclone. So the wind speeds can reach greater than 300 kilometers per hour. They can generate 50-foot waves at sea. They form in tropical waters, specifically the South Atlantic and the eastern Southern Pacific. And the energy comes from condensing water vapor. And they develop most often in the late summer when warm water temperatures provide energy and moisture. So these end up originating where the sea surface temperature is very warm compared to the sea temperatures around that region. So here's the region to the northeast of South America, in the Caribbean, in the Gulf of Mexico, in the Eastern Pacific. This is basically a breeding place for these hurricanes to formulate. So the initial stage of a hurricane is not well understood, but we basically have rating systems to tell how strong a hurricane is. So we would classify a low-pressure cyclone as a tropical depression if the winds do not exceed 38 miles per hour. We would then upgrade that low-pressure system to a tropical storm if the winds are between 38 and 74 miles per hour. And anything greater than 74 miles per hour would be then given a hurricane name. So they diminish intensity when they move over cooler ocean water or they move over land, and the large-scale flow aloft is unfavorable. So essentially, when they run out of fuel, the fuel that keeps a hurricane to form and get larger is going to be the warm, moist air of the ocean. So as soon as you lose that, as soon as you go over cooler water or you move over cooler land, you're essentially taking away the gasoline that keeps the hurricane going. This is just an example showing you a hurricane and giving you isobars on this weather map. So you're going to see near a hurricane, the pressure gradient force is huge. You're going to see that because the isobars are really close together, that indicates a huge pressure gradient force. And anytime you have a pressure gradient force that large, you're always going to have severe weather forming. So the destruction from a hurricane, so there's several factors that affect the amount of damage. So of course you have the strength of the storm, you have the size and the population density of the area that's affected by it, and the shape of the ocean bottom near the shore. So we use the Saffir-Simpson scale to rank the relative intensity of hurricanes. So we have categories of hurricane damage. If you ever hear weather report where they talk about storm surge, this is a large dome of water that sweeps across a coast when the eye makes landfall. That could do a lot of damage because some areas near the coast aren't reinforced for this surge. You can also have wind damage, and you can have inland flooding from torrential downpours. This is an example of a storm surge destruction. As you can see, some of the houses that were up on, they're raised a little higher off the ground, they seem to survive, but anything along the ground, this essentially was all covered with water when the storm surge came in. And that's the end of chapter 19.